Swayam Prabha. Digital India. Educated India.
Okay, so welcome back everyone. I hope you all were able to play around with the code in the first session, and I hope that you were able to produce the candy wrapper effect. If not, then maybe we are going to discuss it now. So the candy wrapper is a very common phenomena which appears in linear blend skinning when two very different rotations are blended. The issue is that many times when you blend rotations, the blended transformation turn into a transformation which is not a rotation. So for example, take these two transformation, and it's an extreme case, but if you blend these two transformation, let's say that the weights of both of the transformation is 0.5. So the transformation you are going to get is T, and you can see that it's a singular matrix, and it's a rank 1 matrix, and it's not a rotation matrix at all. And due to this, when you apply this transformation on a vertex, this volume shrinking happens. Now, in general, for any two rotation transformation T1 and T2, the linear blended transformation does not belong to the space of rotation transformation. But still, the LBS linear blend skinning is a very popular tool in shape deformation. And there are two important reasons behind this. One is the simplicity of the algorithm, due to which it's very easy to understand. And then second is its efficient implementation, which makes it suitable for real-time applications. So the most severe issue with LBS is the treatment of rotations, which we have seen. Ideally, we would want a representation for the rotation that can be fitted in the linear blend skinning framework, but without producing candy wrapper effects. So we are going to see another representation for rotation known as quaternions, which while allowing linear blending, mitigate these issues such as candy wrapper and volume shrinking. So start with quaternions. So quaternions have got an interesting history of their own. They're starting from their conception. Quaternions were invented by Sir Hamilton in 1843, and there is an interesting story about it. He was trying to generalize complex number to 3 dimensions. For example, number of the form s plus xi plus yj. And when he was trying to do that, the math was just not working out. So then on one fine day, he was on a walk in Dublin, where he realized that instead of using 3 numbers, he needed 4 numbers. And he actually carved that idea there on the stone of the bridge. And there is a plate at the same place regarding this historic event. But despite being conceived so early, quaternions were not a very popular choice till recently. And if you are into history of mathematics, it might be interesting to know about it. But today, let's just dive right in. So let's say H represents the set of quaternion. A quaternion Q in this set is represented by a scalar part and a vector part. So S is the scalar part and V is the vector part. The V belongs to a vector in Antri, and S belongs to a real number. Now the relation of a scalar and vector part is similar to the complex number where ijk represents the imaginary unit uh, and which when squared are equal to -1, and the relation between ijk is given by if you multiply I with j, you end up getting k. And this relationship is not commutative, so when you multiply j with I, you end up with -k. So when we say quaternions, these are the elements we are talking about. Now let's define some operations on quaternions, on the set of quaternions. So let's say that Q1 and Q2 are two quaternions represented by S1. So Q1 is represented by S1 and V1, and Q2 is represented by S2 and V2. So the addition is defined simply by adding scale component and vector component separately. So you add up the scale component S1 plus S2, you get the scalar component for the added quaternion, and similarly for the vector part. Now, using the basic definitions of quaternions, we can define multiplication also. So again, you multiply S1V1 to S2V2, and this is by definition. If you expand this expression and if you rearrange the expanded term into scalar and vector part, you end up getting this. It's a very simple algebraic exercise. So as a final expression, you end up with this expression where uh, dot over here represents the dot product between two vectors, and the cross over here is going to represent the cross product between these two vectors. So this is how we are going to define multiplication between two quaternions. Now another important operation is conjugation, and conjugation intuitively is similar to the reversing whatever a quaternion is doing. So quaternion, if Q is the quaternion, then conjugation of quaternion Q is represented by Q star, where scalar part remains as it is and the vector part is negated. And hopefully, when we see the relation of quaternions with rotations, the physical intuition behind conjugation will make more sense. Then we can also define norm on the set of quaternions using the conjugation, which happens to be mathematically same as the usual Euclidean norm. Now, for representing rotations, we are only interested in a subset of quaternions, which is the set of unit quaternions. Now, unit quaternions are quaternions with norm 1, and we are going to represent unit quaternions by H1 in coming slides. Now, to understand the relation between rotation and quaternions, we are going to need two propositions. The first one says that for any unit quaternion Q, a vector n exists such that the quaternion can be represented by Q cos theta and n sin theta. So cos theta is the scalar component and n sin theta is the vector component. So there can be two cases. For the first case, let us say that Q is equal to mm, 1 comma 0. 1 is the scalar component and 0 is the vector component. So if this is the case, then n can be any unit vector and theta is assigned to be 0. This is a trivial case, so nothing interesting about it. But for all other cases, when Q is not a trivial quaternion, then the then n is given by dividing the vector v by its norm. So let's say that k is the norm of the vector v. So n is given by uh, uh, dividing v by norm of vector v, which is k. So we can represent v as k into n, and it's easy to verify that n is a unit vector. Now, since q is a unit quaternion, the norm of this vector is equal to 1. And if you substitute the value of norm from the basic definition, we end up with 1 is equal to s square plus v dot v. We have squared the equation because it is not going to impact both the sides. So if we put the value of v, which is kn, in this expression over here, because n is a unit norm vector, so the dot product of a unit two unit vector is going to give you norm 1. So we end up with s square plus k square. So this is the equation we get, and from basic trigonometry we know that this is an equation for circle. So we know that cos squared theta plus sin squared theta is equal to 1. Now, so that means that there exists a theta between minus pi to pi such that s is equal to cos theta and k is equal to sin theta. So which proves which concludes the proof for this proposition, and for any given quaternion k which is unit quaternion, we can represent this quaternion in a form of cos theta and sin theta. Now, while this proposition should give you some insight into the relation of quaternions with rotations, specifically the axis angle representation, the story is not complete yet, because we have not introduced how the quaternion rotation works. For that, we need another proposition. So let's say we have a unit quaternion Q, which can be represented by cos theta and sin theta using the previous proposition. Let's assume that R is the vector in R3 which we want to rotate. So to rotate the vector R, we need to represent it in the quaternion form. And this quaternion form is represented by P over here, where 0 is the scalar part and R is the vector part. Now the proposition says that the rotated quaternion P dash is given by Q multiplied to P, then multiplied to Q conjugate. Now there is a nice geometrical interpretation of how this expression is obtained, which is related to the reflection of quaternions. But today we are just going to verify it algebraically, and we are assume that we know that this is how you rotate quaternions. So the proposition says that P dash given by Q P Q conjugate is a rotated version of P about an axis n by an angle 2 theta. And the important thing is the angle 2 theta. So in some sense, when we want to rotate a vector by a quaternion, while designing quaternion, we need to half the angle of rotation. Now, to prove this, we will first describe how we can explain a 3D rotation using simple algebra. And then we will show that the quaternion rotation provides us with a similar expression. So let's start with rotating a vector r by an angle phi about an axis n. So this is the vector r and we want to rotate it by angle phi. So the vector r can be represented by its component along an orthogonal to vector n. So let's represent these component by r parallel and r perpendicular. So r parallel is just the projection of vector r onto the vector n. So this is r parallel, and r perpendicular is r minus the parallel component, this, which is this component over here. So you can write r as sum of these two components. Similarly, let's assume that r dash is your rotated version of the vector r, which we want to find out. And we can also write r dash along parallel and perpendicular component to vector n. Now let's represent these two components by r dash parallel and r dash perpendicular. Now important point to note here is that it's only the perpendicular component of r which is going to be affected by the rotation, and the parallel component is going to remain as it is. So r parallel is going to remain as it is, and r parallel then is equal to r dash parallel. So we just need to find out r perpendicular component, I'm sorry, r dash perpendicular component to know the rotated vector r dash. For this, let's consider a coordinate frame that consists of vector n, r perpendicular, and k. Now, uh, k is a vector which is orthogonal to both vector n and r perpendicular. One can write k as a cross product between n and r perpendicular. And if we simplify it a bit, we can write it as a cross product between n and vector r. Now, using this coordinate frame, which is this coordinate frame, we can write r dash perpendicular by r cos theta and k sin theta, which is using basic trigonometry. So you project one component on the r axis, and then you project another component on the k axis, and you get your decomposition. Now, Now we just substitute the basic definitions which we know in this expression over here. So we know R dash parallel is equal to R parallel, and then we put the value for R dash perpendicular, uh, the expression. So this is the expression you get. Now R parallel is just the projection of R onto the vector n, and similarly if you put the value of R and R in this expression, you end up getting this. Now if you expand this term over here, yeah, you multiply cos with R and then to the second term, so you end up getting this. And if you rearrange the terms, this is the final expression you get. So this is yeah. So for your information, this is the Rodriguez formula in a different form. So you can check out the Wikipedia page for Rodriguez formula, and you will see that this is the formula you get in the derivation. The only thing which remains now in the Rodriguez formula is to represent the multiplication, the cross product as a product between the skew-symmetric matrix and the vector, and you will end up with the Rodriguez formula which we have used earlier. Okay, so now this is the rotation which we get after rotating the vector r by by an angle phi and about an axis n. Now let's just check what does our quaternion multiplication provides using the definitions. So P dash is Q P Q conjugate. We put in the value for Q P and Q conjugate. So this is SV 0R and then S and minus V. Now uh, if you expand this term using quaternion multiplication, this is the expression you get. And maybe it's a good idea just to do it on your I mean, you can just grab a pen and paper and try it out on your own side. So it should not be very difficult to try it out, but let's just take a look what are the steps. So this is what you are going to get if you multiply these two quaternions and then again multiplying this quaternion and the resulting quaternion over here, you end up with this expression. Now if you take a closer look, this term over here end up being 0 because if you take a dot product, so if you dot multiply v with a vector which is orthogonal to it, you end up with 0, and then this term is equal to this term and you end up with 0. Also, if you simplify this expression over here, you end up with this. And simplifying this a bit, so let me just iterate it through one by one. So if you open this bracket, this is s square r and minus s r cross v, and then rest remains as it is. Now you can open this term over here, and then you will end up with this. Now there is a triple cross product, and if you over here, if you open this, so you will end up with this expression. And unfortunately, there is no physical intuition about it. It's just plain simple mathematics. You have to do it. And this is a term you get if you add similar components and if you simplify a bit more. Now, because Q is a unit quaternion, we know that the scalar component can be represented by cos theta, and the vector component can be represented by n sine theta. So we are just going to put these values in place of S and V. And this is what we do over here. So if you simplify a bit, you get this, and then if you simplify more, you end up getting this. So this is the final expression, but this is the rotated quaternion. It's not. I mean, it's the rotated quaternion, and you have to get the. We are just interested in the vector part of it because that is how you 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 design the quaternion from the vector you wanted to rotate. So for when we wanted to rotate vector r, we converted it into a quaternion which was represented by p, and this is and now because this is the rotated quaternion, so now to get the rotated vector r, we are just interested in the vector part of it. So so yeah, this is the output we get from the first case, and this is the output we get from the quaternion multiplication. And if you take a close look, this is not very difficult to find that phi is equal to 2 theta. Everything else is same. It's just the angle of theta is angle of rotation is twice. So for a rotation by angle theta, if you are trying to make a quaternion, this is how you are going to define the quaternion. So because you are going to implement it in the next session, in next lab session. So these are the 4 steps you need to perform. First one is given a axis angle representation, which is given in form of theta and the vector n. You need to create a quaternion, and then you need to convert the vector r into a quaternion. Then you have to perform the quaternion rotation, and then you have to extract the rotated vector r. Now let's talk about the blending part.